Okay, so in celebrating Spitzer's birthday today, we are on a journey from the near solar neighborhood all the way out to extragalactic distances. And on this particular stop, we're going to take a step out to about a couple thousand light years away to where the star-forming regions lie. And you can see an example here in the background of the NGC 2264 cluster. Here there is molecular cloud material as well as some stars that have recently emerged from the gas, and we can observe those with Spitzer and now with optical telescopes. I'll explain that more in a little bit. Now, on this occasion of Spitzer's 10th birthday, I've got to admit upfront to you that there is a certain recurring theme that will pop up in this talk, and that is how young stars with disks are like candles in birthday cakes. Before I actually begin, I need to acknowledge many of my collaborators who have contributed to the material in this talk. At Caltech and JPL, we have a small and energetic group that works on young stars and their variability. We're also part of two large collaborations with too many people to list, but if you'd like to learn more about the Young Star Stellar Object Variability Project, or YSOVAR, as well as the CSI 2264 project that I'll be talking about later in this talk, you can visit the websites listed here. I want to begin by showing a just phenomenal image of the NGC 2264 cluster, which is the subject of my talk. This was taken with Spitzer's IRAC and MIPS instruments at 3 to 24 microns. Since its launch about 10 years ago, Spitzer has contributed greatly to our censuses and our understanding of young stars. At about 1 million years, the end stages of star formation and planet formation coincide. Now, Spitzer has enabled us to peer inside these molecular clouds, an example of which you see here, to not only find out where the stars are, but to measure their properties. And I wish I had more time to go into these population studies of young stars, but that's a whole nother subject that I won't have time to get into. So what we're going to do instead is, in this celebration of Spitzer's, to zoom in on individual stars and see what Spitzer has taught about them over the past 10 years, and specifically what we have learned about their behavior over time. So what do we know about young stars at these ages of 1 to 5 million years? First of all, they are magnetically active. They have spots on their surfaces, many of them do, kind of like sunspots, but much larger. These are created by the strong magnetic fields on their surfaces. Those magnetic fields also link them to surrounding circumstellar disks, which are the remnant material left over from the star formation process, dust and gas, which may eventually form planets. There is also ongoing gas accretion in these objects, whereby material flows from the surrounding disk onto the star. So, what do all these properties mean? Well, these stars are highly variable on many time scales, from hours to days, months, and even years. This becomes a little more obvious when you visualize what is actually going on in the vicinity of these stars. Here's a schematic you can keep in mind. You see a star in the center connected to a surrounding disk by a magnetic field, which then allows the material to flow from the inner disk rim onto the central star. Now, there is emission at quite a variety of wavelengths, as you can see here, depending on the temperatures of the different regions. Where material hits the central star and forms an accretion shock, you have very, very hot gas, which emits in the UV and even X-ray. The star itself is emitting primarily in the optical and a bit in the near infrared. The further out you go in the disk, the longer the wavelengths of emission become as the temperatures are cool there. Now, the Spitzer Space Telescope is now in its warm phase. And so the observations are only done at 3.6 and 4.5 microns, and those wavelengths correspond to the region around 0.1 AU, which is close to the inner disk rim. Now, this is a very interesting region, and a lot of unanswered questions exist surrounding this area. And those questions, which have to do with the configuration of the magnetic field, how the material flows, and what the structure of the inner disk are, have ramifications for the early evolution of the star, as well as planet formation, which may be taking place in this region. So let's look a little bit in more detail about some of those difficult to answer questions. What is missing from our picture of young stars and their inner disks? And so here are three broad areas that I'd like to highlight, one of which is the structure of the inner disk. If you look on the upper left here, I'm showing an example of spiral structure in a disk. Now, this is much larger scales than what I previously mentioned of about 0.1 AU. This is more like the orbit of Pluto, or say 50 AU. This is a direct image which was recently taken of a disk around a young star, and the red dot in the center is actually blocking out the flux from the central star, and unfortunately it's also blocking out our view of the very inner part of the disk that we're so interested in. But I put this picture here to show you that there is non-symmetric structure, at least in the outer disk. You can see a spiral shape here, and the question is, does this structure persist into the inner disk? The schematic I showed you earlier assumed that everything is nicely symmetric and perfect, but that may not be the case at all. Now, I was trolling around the internet looking for some kind of clever cartoon to represent this scenario, and I have to thank the people out there that are making birthday cakes, because apparently they thought of the same idea. Okay, moving on to the second question that we'd like to understand about inner disks is the dust properties are also a very important topic. As young stars begin to spawn planets, we think that the grains within the dust disk surrounding them are evolving to larger and larger sizes, from micron size to eventually centimeter size, until they can form boulders to create stars. And the question is, when do all those processes happen? What is the time scale? And how can we directly observe the dust properties around these young stars? And at any given time, we'd like to know what size the dust are, or if we think of it in terms of a birthday cake, are there big grains, small grains, or is everything uniform? Okay, you can probably guess where this is going now. And the last question that I'd like to briefly mention is, how are the star and the disk actually connected? And again, thinking back to the schematic I showed you, there was a very simple magnetic field there, but in reality, its configuration may be much, much more complicated. And we'd like to know how that affects the flow of material from the disk onto the star, and maybe how it affects the formation of planets. Here is another cake to represent this complicated scenario. Now, you might be wondering why can't we just image the inner disks? Can't we just take pictures of them and learn what the structure is, what's there? Well, the problem is that, in fact, looking at these disks, as they are now, the reality is that they are very, very far away. So, in fact, our spatial resolution is just not good enough to image the regions of interest, and we need something else to learn what's going on here. That something else, I'm going to tell you about, is time series photometry, whereby we can actually probe structures in the inner disk as they orbit around the central star as a function of time. Now, within the past 10 years, since the launch of Spitzer, we've had a revolution in time series monitoring of young stars, both in the optical and in the infrared. I'll briefly highlight what has happened in the optical before going on to Spitzer. There have been two main space telescopes that have been monitoring young stars, MOST and COROT. Those are Canadian and French missions. You may have heard of Kepler as well, which I'm not going to talk about because it does not look at young stars, or at least it has not yet. So previously, optical monitoring of young stars did confirm that they are highly variable, but due to the constraints of ground-based observing, such as bad weather and the fact that you cannot observe during the day, we had very partially filled data sets. An example of which you can see here are 4 stars that were monitored from ground-based telescopes over the course of a few days. And we could tell they were variable, but we couldn't tell much else about them due to the gaps in the data set. Then came along MOST and COROT, and the difference in the data is just phenomenal. You can make out all the blips in the light curves, and for the first time we can say not only is something variable, but what type of variable is it? What sort of flux changes does it have? Are they predominantly in the downward direction, upward direction? Some examples you can see here. Now, at the same time, when Spitzer launched, we started to get interested in what sort of flux variations are these young stars showing in the infrared, because this has implications for what's going on in the disk where the infrared emission comes from. Now, the naive assumption was, well, the disk is just sitting there, not really doing much, and so we shouldn't see variability in the infrared, or it shouldn't be particularly interesting. There were a few hints that maybe that assumption was wrong, but prior to Spitzer, there really was not any significant monitoring of young stars in the infrared, unlike the optical, which we can do successfully from the ground. And so we really had no idea what these stars might reveal when looked at with Spitzer. So in 2009, there was a pilot project just before the cryogenic mission of Spitzer ended to look at some young stars in the IC 1396 cluster. And what did we find? Well, amazingly enough, a number of these young stars, 4 of which are shown here, were variable at the 10, 20, 30% level, and that was quite a big surprise. What was causing that variability? Initially, it was quite a mystery. So this launched the Young Stellar Object Variability Campaign, which is a warm Spitzer project to look at about a dozen different clusters where these young stars reside at the 3.6 and 4.5 micron bands with the Spitzer telescope. Now, shown here are some of the amazing light curves that we uncovered in the Orion Nebula cluster, shown at left. And you can see that, as hinted at by the IC 1396 initial observations, indeed these young stars are varying in the infrared and sometimes quite wildly with a number of very interesting patterns. What could be causing this variability? Well, one of the most popular explanations so far is changes in the inner disk scale height. What do I actually mean by that? Well, if we go back to our example of a cake, here is a cake representing a disk. Now, there's no star in the middle, but you can imagine it. And the inner rim is this area toward the inside of the cake where the frosting is a little bit higher than the outer parts. As you can see on the right side, there is a shadow behind that rim of frosting because there is a light source illuminating it. Now, what happens if we were to actually bring that rim up and down? As you can imagine, the shadow would get deeper and it would extend further back onto the cake. This is, in fact, what may be going on in these young stars as an inner rim goes up and down. And I'll show you a side view schematic here. The inner rim is represented by the red bars here. As it goes up and down, you get more or less shadowing onto the outer part of the disk. As a result, the spectrum at longer wavelengths increases, and at shorter wavelengths, where the rim is, it decreases as the rim goes down, and the reverse happens when the rim goes up. So this is one explanation invoking some specific dynamic mechanism in the disk to explain some of that variability. Now, in reality, in order to understand the causes of this variability, We need not just infrared, but we need infrared optical in as many wavelengths as we can get our hands on simultaneously. So what do you get when you combine exquisite space telescope data from Spitzer, Corot, MOST, and a handful of other telescopes? You get the Coordinated Synoptic Investigation of NGC 2264, or CSI 2264 for short. Now this was a project that was initiated in 2011 with the goal of finding out how the behavior of young stars differs at various wavelengths. And as you can see here, we used a number of telescopes monitoring at high precision for 30 or more days in most cases, which was a truly unprecedented campaign. Well, so you're probably wondering, what do these light curves of young stars actually look like, and what can they tell you when they are taken simultaneously from so many exquisite telescopes? Well, we are in for a few surprises. It turns out that although the goal was to see how the behavior of these young stars is related at different wavelengths, in many cases it's not related at all. Here I show some examples of light curves taken over 40 days from the Corot Space Telescope in black and from Spitzer's War Mission in blue and red. Marked with vertical lines are times when high-resolution spectra were taken with the ESO Very Large Telescope. All of these light curves have had their mean magnitudes shifted so that you can see them all in the same plot. So as you can see here, in many cases there is interesting or perhaps periodic behavior in the optical with Corot in black, and there's something totally different going on in the infrared. This tells us that there are probably multiple variability mechanisms affecting the flux behavior that we see in these objects. There were also some other surprises. You might expect, in some scenarios, for optical and infrared behavior to be similar, but to display phase lags or out of phase behavior. And such a scenario might be if you have a hot spot on the center of the star. As it rotates into view, you see a brightening of the star. But as it rotates out of view, it heats up the back part of the disk rim, which would then be in your line of sight. And so 180 degrees out of phase, you might expect to see a brightening of the disk in the infrared, so that the infrared and the optical light curves would basically be shifted with respect to each other. That's a scenario that seems very natural for these objects, and we expect to see a lot. But in fact, there are only 2 objects in a data set of about 200 that we examined. And of course, there are about 1,000 objects altogether that we observed in this young cluster, NGC 2264. So out of all those objects, we only found 2 examples shown here, where the light curves seem to be slightly shifted with respect to each other. And that's quite a surprise. In addition, we found other examples where there wasn't much at all going on in the optical. The light curves were essentially flat, but in the infrared there was high amplitude, so 20-30% changes in the flux behavior, which cannot be linked to the star at all, because the star would be doing something in optical if that were the case. So here you see again in red and blue the Spitzer wavelength behavior. And in these cases, these might be prime examples of where there is dynamic behavior of the inner disk rim, perhaps caused by magnetic turbulence or some other property of the disk. So what could explain the variety of infrared phenomena that we're seeing in these young stars and their disks? Well, viewing angle is very important. And as you can see from these disks here, whether you're looking face on or edge on or something in between with respect to the star and its disk can be important. Why is that? Well, the light from the central star, represented by a candle here, shines and also creates shadows on different parts of the disk. So if you're looking face on, most of the disk will be illuminated. If you're looking edge on the other hand, you're going to see different reflections from the scattered light as it comes from the star and bounces off different parts of the disk. So depending on the orientation of the disk, you're going to see enhanced emission at different wavelengths. Now, our colleague Neil Turner at JPL has modeled this effect, and he has also modeled the effect of what happens when that inner disk rim moves up and down and how it changes the emission at different wavelengths. Here he has modeled the optical V-band, near-infrared J-band, and mid-infrared from Spitzer at 3.6 micron band, all combined together into an image of a disk and a central star, viewed at 60 degrees inclination, so not exactly edge on and not face on either. So here is a case where the disk is relatively flat, and he shows how the different parts of it emit at different wavelengths, and he's combined them here to represent them with a color. Now if instead the inner disk rim rises up, and he has caused that to happen by injecting magnetic turbulence into the inner part of the disk where it is ionized by the star, then what happens? You can see that the color changes and it becomes much more red in the outer disk, and it becomes much brighter in the inner disk where this inner rim has popped up. Now, if we show the two images in sequence here, you can better appreciate how those color changes. So again, this supports the idea that when the inner rim moves up and down, you get color changes in the optical through the mid-infrared emission of these disks. Now, at higher disk inclinations, one prediction is that we will actually be looking through some of the dusty material in our line of sight to the star. And what would happen then is that if there are inhomogeneities in the disk, such as blobs or warps, we would see them periodically occulting the central star. And that's what we think we're seeing in this case, this set of light curves here, again from Corot and Spitzer. You can see these periodic dips in the light curves that are almost like eclipses, but they're not as regular and they're varying in depth. What we think we're seeing here is blobs of material that are orbiting the central star, and whenever they pass between the star and our line of sight, then the star appears to become dimmer because part of it is being blocked. Now, these systems are rather interesting because we can learn about the dust properties that of the material that we are actually looking through. And here is a picture of a cake again. Here is another example of one of those systems in which we are looking, we think, through these blobs of dust in the disk. And now I have colored the Spitzer light curve in red and the Corot light curve in blue. And what I have done with the Spitzer light curve is I have scaled it up so that it matches the amplitude of Corot. In reality, the amplitude of the Spitzer light curve is lower, but I have multiplied it by a factor of about 4 to match it up. Now, that factor of 4 is actually quite important because it tells us how much more light is being blocked at the infrared wavelengths compared to the optical wavelengths. And we can compare that to the case if we had standard interstellar dust that we know about from just observations of around our galaxy. That factor would not be 4, it would be more like 20. So what does this tell us? It tells us that this dust that is in the central region of the disk is a lot less efficient at blocking the infrared light coming from the central star along our line of sight than regular dust is. And that in turn implies that this dust has probably had substantial processing on its way to forming planets, so that the grains are much larger than the standard interstellar ones that we know much more about. And the interesting thing about these systems, and there's another example that I show here, is that as we go to lower and lower mass central stars, the dips actually seem to become deeper in the infrared than the optical. So in blue and red here, you can see that the events have larger magnitude decrements than in the optical. And we're not really sure why that is, except that it may be related to different dust properties around the lower mass stars and the brown dwarfs. And that will be something that requires more investigation to learn about. There is certainly more modeling to be done, and we'd like to learn more about the grain properties in our disks. Okay, so looking toward the future, it's been a great 10 years of Spitzer, and we hope for many more. Thanks to this infrared telescope, we now know that not only are young stars highly variable, but so are their disks. Some of that infrared variability could simply be from reprocessed starlight, but as I showed you, in many cases it doesn't correlate well with the stellar variations, and it has to be coming from the disk itself. The typical timescale for infrared variability is just about 5 days, which is too short in many cases to be explained by disk orbital dynamics. And so we think, as I mentioned, that this may be caused by the inner rim of the disk moving up and down by various mechanisms. That's one potential idea, but other explanations await. We'll be following up some of the interesting variables that Spitzer discovered and that I showed you, and possibly looking to see how they behave on longer time baselines. So stay tuned for further results from the full set of young stellar object variability project clusters and also from the CSI project. Thank you.